Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up chapter 11 by taking a quick look at section 11.11 from your textbook. In this video, what we're going to be taking a look at is trying to understand the errors when we use a Taylor polynomial to approximate a function. In sections like 11.8, 11.9, and 11.10, our goal was coming up with a direct equality, a power series representation of functions. And we saw that to do that, we could take a function and represent it as an infinite polynomial. Of course, sometimes in practical situations, we don't want to have to carry around an infinite polynomial. We're just going to use a finite polynomial. Because we're just going to use a finite polynomial, it's not going to be an exact equality, but it's going to be an approximation. And we're going to look at the accuracy of those approximations. So the first two definitions here, we actually already discussed these at the end of 11.10. We said that the Taylor polynomial of degree k is the truncated Taylor series where we run from n equals 0 up to k instead of n equals 0 to infinity. That makes it only have degree k because the highest order polynomial term will be x minus c to the k. And then remember that we said the kth degree remainder term is the difference between the function and that Taylor polynomial of degree k. Then we also talked a little bit about this sort of important inequality that can be used to prove that a function is equal to its representation, called Taylor's inequality. But we're going to be using that Taylor's inequality mostly to understand the accuracy of these estimates. So remember, Taylor's inequality said that if the absolute value of your k plus first derivative of x is less than or equal to m for all x in the interval that you're working on, then the remainder term in absolute value is less than or equal to that m over k plus 1 factorial times x minus c to the k plus 1 for k minus c less than or equal to d. And then that's giving you the interval that you're working on. Now, before we get into some examples, I'd like to take just a little look at this because this is very similar to some of the error-bound things that we did back when we were doing approximate integration, and just talk about each of these components. So, in sort of words, this m up here, this is an upper bound on the absolute value of the k plus first derivative of our function on the interval. So, to determine m, what you're going to need to do is you're going to need to find the k plus first derivative, put it in absolute value. So again, we don't care about if it's positive or negative. We just want it the largest magnitude. So we want an upper bound on the absolute value of the k plus first derivative, so the largest magnitude of the k plus first derivative on the interval that we're working on. And the interval is going to always be specified. It's just going to be the interval that we're trying to make our estimates on. This k plus 1 factorial, that should be just clear. That's just going to be based on whatever sort of degree polynomial you're using. So the larger the degree polynomial, the larger this is, which will mean that this overall is more accurate. And then this x minus c to the k plus 1, this is sometimes the most confusing for people because this inequality is actually a functional inequality, talking about the size of this function versus this. But in terms of practical use, what you're going to do with this component is that this x minus c in here, this is going to be just replaced with the sort of size, or we'll even use the word radius, with radius of interval being worked on. So this is actually a functional inequality, meaning it's comparing two functions. But for practice, when we're actually using it, what we're going to do is we're just going to simply say, well, we want to sort of know the maximum error. So we'll take whatever the sort of size of the interval is. We'll say that that's the maximum that x could be away from the center. So we'll use that to replace that x minus c. So you can, this is how Taylor's inequality is phrased. But you guys can just remember that that x minus c is just going to be replaced with the radius of the interval that we're working or doing our estimates on. And then, of course, this k plus 1 exponent there, well, that's again just based on whatever degree polynomial you're using. So that hopefully helps a little bit understanding what these components are. Now let's take a look at some examples where we'll build some Taylor polynomials and then measure the error that would be the maximum error if we used one of those Taylor polynomials to estimate something. So let's take a look at our first example here. We're going to consider the function f of x equals ln x. We're going to write down t2, so the second degree Taylor polynomial for this function centered at x equals 1. Then we're going to use T2 to approximate ln of 1/2, and then we're going to determine the maximum error for approximating f of x on the interval 1/2 to 3/2. So we're going to just talk about what sort of maximum error on this interval. You'll notice that whenever you look at these questions, the interval is always going to be centered at the center, because that's how we always think about sort of doing these estimates here. All right, so let's talk about how we're going to deal with A. To build T2, what we're going to do is the same thing that we were doing when we were trying to build the Taylor series, but we don't have to worry about finding a general pattern. We literally just need to get to whatever degree is specified. So in this case, we will make our table 0, 1, and 2. That's all we're going to need, because we're just going to need T2. Then we'll have to get the nth derivatives there. Of course, we'll only have to get the first column. We'll put ln x right here. Then the derivatives evaluated at the center, which is going to be 1. Then those derivatives evaluated at 1 divided by n factorial. And then the derivatives evaluated at 1 divided by n factorial times x minus 1 to the n. This time, if we see any simplifications, feel free to do it, because again, we're not looking for a general pattern. We're literally just looking for the second degree polynomial that approximates ln x. So derivatives here should be pretty easy. First derivative is 1 over x. Then treat this as x to the minus 1, differentiate that, and you get minus 1 over x squared. Okay, let's go ahead and plug in 1 into this. Well, ln of 1 is going to be 0. 1 over 1 is going to be 1, and negative 1 over 1 squared is going to be negative 1. Then, looks like we should get 0 here. Then we're going to get 1 divided by 1 factorial, which of course, sorry about that, is just 1. And then minus 1 divided by 2 factorial is going to be minus 1/2. So then we're going to get 0, 1 times x minus 1, and minus 1/2 times x minus 1 squared. So what we can then say is that T2 of x is equal to 0 plus x minus 1 minus 1/2 times x minus 1 squared. Whenever you're writing out Taylor polynomials, just leave it like this. Don't expand anything out, because we want to see that center that we were using. Remember, we specifically did this for it being centered at x equals 1. So you want to make sure that you have it actually where it shows the center that you were using. So don't simplify this at all. Just leave it as is. So there's T2. All right, how would we use this to approximate ln of 1/2? Well, what we would say is that we'd say ln of 1/2 should be sort of roughly similar to T2 of 1/2. So ln of 1/2 would be something we'd probably have to compute using a calculator, but T2 of 1/2 is something we can sort of do by hand. Of course, in this class, you're still welcome to use a calculator, but you should be able to recognize that T2 of 1/2, plugging 1/2 into here, is just going to be arithmetic. If we do that, we would get 1/2 minus 1 minus 1/2 times 1/2 minus 1 squared. And if we do that, we can get that ln of 1/2 is approximately, looks like this should give us negative 1/2. This here is going to give us negative 1/2. If we square that, it sounds like 1/4, and then times a negative 1/2, it's going to be negative 1/8. So negative 1/2 and negative 1/8, that sounds like we're going to get negative 5/8. So we're saying ln of 1/2 is roughly, what is negative 5/8? Like negative 6.75, I believe. Let me just check that and make sure. Oh, negative 0.25, sorry about that. Okay, so there we go. We've used our Taylor polynomial to come up with an approximation of ln of 1/2. Now again, we don't expect that to be super accurate because we only did T2, but you can sort of see the power of this, right? If you wanted to figure out ln of 1/2 to a good degree of accuracy, you just need to extend this polynomial, do a few more derivatives, plug in 1/2, and then you can just do it via basic arithmetic. Actually, behind the scenes, what your calculator is doing when you type in ln of 1/2 is using this Taylor approximation, maybe not this specific one, but using a power series representation to come up with that approximation just at a very high degree of accuracy. Because remember, computers, calculators, things like that, very good at doing massive amounts of arithmetic so that they can use that as a way of calculating these more complex values. All right, One more thing, let's determine the maximum error for approximating f of x on the interval 1/2 to 3f using t2. So what we want to do is we want to look at using Taylor's inequality. So since we're using t2, we want to talk about r2 of x in absolute value. And we're going to say that that is less than or equal to, so we're doing k equals 2 here. So we're going to look at this expression. So that means we're going to have less than or equal to m over 2 plus 1 factorial, and then x minus 1, because our center is at 1 here, and then the exponent is also k plus 1. So we have 2 plus 1 up there. So that's the sort of basic form of Taylor's inequality. Now, the first thing that we can sort of do, based on what we discussed here, is we can talk about how to replace this. Remember, this is replaced with the radius of the interval that we're working on. So in this case, if you think about this interval, 1/2 to 3/2, you're working on it centered at 1, so the radius here is 1/2. So what we can sort of say is, when working on 1/2 to 3/2, this component here, max is 1/2. The most we can be away from the center of 1 when we're working on 1/2 to 3/2 is 1/2 unit away. If you're at 1/2, you're 1/2 unit below. If you're at 3/2, you're 1/2 unit above. So we now know that we can sort of replace this. The largest it can be is 1/2 here. So we can now say that r2 of x is going to be less than or equal to m over 3 factorial 1/2 cubed. Now the question is how to get that sort of m. So let's talk about how we're going to do that. Remember, we'll take this on to the next page, I guess. For m, it will be an upper bound on the k plus first derivative in absolute value. Since we only did t2, right? Since we're looking at r2, since we built t2, we need to go to the third derivative. So what is the third derivative of our function? Well, we don't have to do all 3 derivatives. Remember, we left off by finding the second derivative right there. So we can just differentiate this, and we should be able to see that we would get 2 over x cubed. So that means absolute value of that is also going to be 2 over x cubed. So this max on 1/2 to 3/2, because that's the interval we're talking about. Well, this is a decreasing function, so the larger x's, the smaller this gets. So if we choose the smallest x value, this will be as large as possible. So since absolute value of the third derivative is decreasing, use x equals 1/2. So we'll have m be the absolute value of the third derivative evaluated at 1/2, which looks like we'll get 2 over 1/2 cubed. 1/2 cubed, of course, is 1/8 times that 2, so that's going to be 16. So our m should be 16. So if we then go back to our Taylor inequality, we have r2 of x. The remainder is less than or equal to, well, we have 16 for this now. So we can say 16 over 3 factorial times 1/2 cubed. I guess we can just type that into a calculator. That's going to be 2 divided by 6. So that is going to be approximately 0.333. So what that tells us is when estimating ln x on 1, 2, 3, 2 with t2 of x centered at x equals 1, max error is 0.333. Now, what that's basically saying is that the worst case scenario is that our approximation we came up with here is off by 0.333. Now that's really bad if you think about it, because this is only negative 0.6, so being off by 0.333 is like close to like 50% error, more than 50% error. But of course, we only did this with T2. So we did it a very small approximation, and so this estimate isn't that great. It actually turns out that in reality, if you do type in ln of 1/2 into your calculator, ln of 1/2 is much closer to negative 0.625 than this 0.333 says. But remember, this is a maximum error bound. We're saying that this can be no worse as an estimate than being off by 0.3333. And in fact, this error bound holds for estimating anything on 1/2 to 3/2. So if you estimate ln of 5/4 or something like that, that's also in that 1/2 to 3/2 range, then the maximum error for that would also be only off by at most 0.3333. So there we go. That's how we can use Taylor's inequality to come up with a maximum error when estimating using a Taylor polynomial. Okay, let's go ahead and take another look at this. So we'll try another example here. We're going to consider the function f of x equals x to the 4/3. Very similar. We're going to start by writing down t4 in this case, centered at x equals 8. We'll use t4 to build an approximation for 9 to the 4/3, and then we'll determine the maximum error when approximating this function using t4 on the interval 6 to 10. Okay, so let's go ahead and start with A. Again, we'll make a little list. We'll need to do 0, 1, 2, 3, and 4 because we want t4 here. So we'll need to do the derivatives here, and we'll be starting with x to the 4/3. Then we'll need to evaluate each of those derivatives at 8. Then we'll need to evaluate each of those derivatives at 8 and divide by n factorial. And then we'll build our actual terms, which are the derivatives evaluated at 8 divided by n factorial, and then times x minus 8 to the n. Why x minus 8 to the n? Well, because it's centered at x equals 8. Okay, let's go ahead and get the derivatives here. First derivative, drop that 4/3, x to the 1/3. Differentiate again, 4/9, x to the minus 2/3. Differentiate again, looks like minus 8 over 27, x to the minus 5/3. Differentiate one more time, looks like we get 40 over 81, x to the negative 8/3, something like that. Again, doing the arithmetic here is fine because we're not looking for a general pattern. We just want to actually get the literal values here. Okay, we're going to plug in x equals 8. Every time we have that 1/3, 8 to the 1/3 is going to be 2. So here this is going to become 2 to the 4th, which is going to be 16. Here this is going to become 2 times 4/3, which I guess is 8/3. Here this is going to become 2 to the minus 2, which is 1/4, so it'll cancel out with the 4 and we'll get 1/9. Here, I guess it'll become 2 to the minus 5, which is 1 over 32. 1 over 32 will cancel with that 8, and we'll get a 4 times 27. 4 times 27 sounds like 108 minus 1 over 108. Let's just check that, make sure. Yep, that sounds good. And then here, this will give us a 2 to the minus 8th. 2 to the 8th is 256. And if we do 40 divided by 256 times that 81, it's going to be pretty messy, but we can get it as a fraction there. Looks like you should be able to get it as, like, just using a calculator, 405 out of 32. Okay, so again, we're just trying to get some of the actual values there. Then dividing by n factorial, this is going to be 16. This is still going to be 8/3 because 1 factorial is 1. This one, when we divide it by 2 factorial, is going to give us 1 out of 18. This one, when we divide by 3 factorial, that's dividing by 6. So 108 times 6. I guess that's going to be negative 1 over 648. And this one, we got to divide by 24. So if we do that, let's see. Oh, I made a calculation error back here. Let's go back real quick. Sorry about that. 40 times that 2 to the negative 8, and then divided by 81. A little bit messier than we probably needed here, but that's okay. Okay, this looks like it actually should have come out as 5 over 2592. I think I accidentally did 2 to the 8th rather than 2 to the minus 8. So there we go, some really small value there. And then when we divide that, 5 divided by 2, 592, divided by that 4 factorial, we're going to get something really ridiculous, 5 over 62208. Okay, so pretty horrendous sort of fractions there, but again, all just sort of arithmetic stuff. Now let's make the actual terms there. So this would be 16, and then 8/3 x minus 8, and then 1/18 x minus 8 squared, minus 1 over 648 x minus 8 cubed, and then 5 over 62208 x minus 8 to the 4th. Okay, so there we go. So we now have our actual T4. So T4 of x here would be 16 plus 8/3 x minus 8 plus 1 over 18 x minus 8 squared minus 1 over 648 x minus 8 cubed plus 5 over 62208 x minus 8 to the 4th. So there we go. That's our T4 there. All right, now let's use that real quick. So how would we actually get an approximation for 9 to the 4/3? Well, we would say 9 to the 4/3 should be roughly T4 evaluated at 9, which would be 16 plus 8/3. Since we're plugging in 9 here, all of these are going to just be 1, plus 1 over 18 minus 1 over 648 plus 5 over 62208. If we do that, 16 plus 8/3 plus 1 divided by 18 minus 1 divided by 648 plus 5 divided by 62,208 looks like we should get that thing comes out as about 18.72. So there we go. That gives us a pretty nice approximation for that 9 4/3. If you actually check 9 over 4/3 on your calculator, you actually get a very similar 18.72075,441. So very similar to what our T4 polynomial looked at. Now again, it's messy to do all this, but if you imagine that you didn't have a calculator, this would actually give you a feasible way, maybe time consuming, but an actual way of determining 9 to the 4/3, which otherwise we probably didn't know a way of at least approximating. So there we go. We've gotten another sort of approximation using this Taylor polynomial. Now let's talk about the sort of maximum error when working on the interval 6 to 10. So to do this, we're going to use that Taylor inequality here. So R4 is going to be less than or equal to m over 4 plus 1 factorial, and then x minus the center, which is 8, to the 4 plus 1 exponent. Okay, first thing to do is to figure out how big this could be. Since we're working on the interval 6 to 10, the furthest x could be from 8 is going to be 2. So, working on 6 to 10, largest distance is 2. The most we could be away from our center is 2. Notice that this is basically a fancy way of saying the further you drift from your center, the worse your approximation is going to be. So we can now say that R4 of x in absolute value is going to be less than m over 5 factorial times 2 to the 5th. So we've got that right there. Now we need to determine that m. So let's go on to our next page here. So remember, m is going to be an upper bound on the absolute value of the k plus first derivative of x. Since we're doing R4 here, we need to look at the 5th derivative. To get the 5th derivative, well, we can just take the last one that we had back here. That should be 4 there. I don't know why that got cut off. But we just need to take one more derivative here. So if we do that, we can get that the 5th derivative of our function. If we differentiate this thing, we got to drop that negative 8 over 3. So it looks like we're going to get negative 320 over 3 times 81, it's going to be 243, and then x to the negative 11 over 3 there. Now, of course, we want to put that in absolute value, so we're going to look at that in absolute value, which is 320 over 243. And then we can also imagine getting that x to the 11 thirds in the denominator, because the negative exponent, of course, just puts it down there. Now this is decreasing again. So the larger x is, the smaller this is. So since we are on the interval 6 to 10, well, this is getting smaller and smaller the larger you put in xi. So we want the biggest. So we'd probably use x equals 6. So let's use m equals the absolute value of our fifth derivative at 6. So that's going to be 320 over 243, 6 times 11, 6 to the 11 over 3 power. We'll have to just do that on our calculator. So 320 divided by 243 divided by 6 to the 11 thirds. Looks like that should come out as approximately 0.002. So if we put all that together, we can say that our remainder function in absolute value has to be less than or equal to 0.002, 5 factorial, and 2 to the 5th. Plugging all that in, 0.002 divided by 5 factorial, which is going to be 120, and then times 2 to the 5th, which is 32. Looks like we get that as approximately 0.00053. So we get a minuscule error when using this T4 approximation anywhere from 6 to 10. So we use that T4 to estimate anything like 6.5 to the 4 thirds or 9.8 to the 4 thirds or any value we like between 6 and 10 to the 4 thirds. We know that the error is going to be no more than 0.00053. It could even be less than that, but it will certainly be no more than 0.0053. So max error for estimating x to the 4 thirds with T4 of x centered at x equals to 8 on 610 is 0.00053. So an incredibly small maximum error when using this T4. And this does show you that these Taylor polynomial approximations, they can be quite accurate even for relatively small degrees. I mean, I know that the fractions got pretty messy for T4, but if you think about it, that's only the 4th degree polynomial, and already the accuracy is very high. All right, let's do one last example with sort of another sort of famous function. We never got a chance to build a full series, a Maclaurin series for tangent. It is doable, but it's beyond the scope of our class. So let's build a small Taylor polynomial for it and look at its accuracy. So we're going to consider the function f of x equals tan x. We're going to write down T3 centered at x equals 0. So technically we're writing out the first few terms of the Maclaurin series. So I guess you could call it a Maclaurin polynomial. Then we're going to use T3 to estimate tangent of 1/2, and then talk about the maximum error for approximating negative pi over 4 to pi over 4. So we'll make our little table, 0, 1, 2, and 3. We'll need to look at our derivatives. And of course, our first function, or our function itself, is tangent. Then we'll need to look at those derivatives evaluated at 0. Then the derivatives evaluated at 0 divided by n factorial, and then the derivatives evaluated at 0 divided by n factorial times x to the n, because again, we're doing x equals 0, so the x minus c is just going to be x to the n. Okay, first derivative should be nice and easy. That's going to be secant squared. Then to differentiate this, we're going to have to do chain rule. So we're going to get 2 secant x, and then times the derivative of secant, which is going to give us another secant factor, so 2 secant squared, and then a tangent factor. So we get 2 secant squared tangent x. Then we need to differentiate that again. We're going to have to use product rule. So the derivative here is going to give us 4, then secant x. But then we're going to get a secant tangent, so secant squared. And of course, this tangent is going to stick around, so we're going to get tangent squared. Then we need to differentiate this component, which is going to give us a secant squared. So it sounds like 2 secant to the 4th x. Okay, so there we go. 4 secant squared tangent squared, 2 secant to the 4th. If you're a little unsure of how we went from here to here, just write it out separately, take a little bit more space to do it, and you can confirm that this does give you this as its derivative. Okay, now let's plug in 0. Remember, when we're plugging in 0, tangent of 0 is 0, and secant of 0 is 1, because 1 over cosine is secant, 1 over cosine of 0 is also going to be 1. So actually plugging in 0 is going to be very easy. 0, 1, 0, and here, this is going to be 0, but this is going to be 2. So it looks like we get 0, 1, 0, 2. Then we got to divide by n factorial. So this will be 0, this will be 1, this will be 0, and then this will be 2 divided by 3 factorial, which is the same as 6. So it sounds like 1/3. So we're going to get 0, then x, then 0, then 1/3 x cubed. So interestingly enough, what we get is that t3 of x here is actually x plus 1/3 x cubed. We should not be shocked to see that we only got these odd terms. Remember, we're now working around x equals 0, and tangent is an odd function. Right? Tan of negative x is the same as negative tangent of x. So it makes sense that we're only getting those odd exponents. Anytime you're centered at 0, that even-odd geometric definition fits the even-odd that we actually get as the exponents here. So we got t3. Okay, so let's use t3 to do an approximation then. So that gave us a here. So for b then, tangent of 1/2, well, we could say tangent of 1/2 is going to be roughly the same as t3 of 1/2, which should be 1/2 plus 1/3 times 1/2 cubed. And if we do that, again, obviously you could just do this by hand, but I'm going to speed it up a little bit. That should come out as about 0.542. So tangent of 1/2 should be roughly 0.542. If you actually check that by typing in tangent of 1/2 on your calculator, you will see you get about 0.546. So it's not a perfect estimate, but it's pretty decent for the fact that we did this with only 2 terms. And again, this would be a relatively easy calculation to at least get a rough estimate of what tangent of 1/2 would be. Okay, let's figure out the maximum error when approximating on negative pi over 4 to pi over 4. So we need to look at R3 of x using Taylor's inequality. We know that that's m over 3 plus 1 factorial, and then x in absolute value to the 3 plus 1. Now, since we're working negative pi over 4 to pi over 4, the furthest we could drift from the center of 0 is pi over 4. So, on negative pi over 4 to pi over 4, the max distance from x equals 0 is pi over 4. So, we can replace that with a pi over 4. And we will get that the absolute value of the remainder term needs to be less than or equal to m over 4 factorial times pi over 4 to the 4th. So there we go. That's the start of our remainder. Now we got to go figure out our m here. So one last page here. We'll need to go grab the derivative. Now this derivative was messy enough, so let's go just grab that we did this here, and we'll need to differentiate it one more time. So let's just go put this here. So remember, this was n equals 3. So m is going to be an upper bound on the absolute value of the 4th derivative on the interval negative pi over 4 to pi over 4. So we need to take one more derivative here. So the 4th derivative. Well, we're going to have to do some product rule here. Derivative here is going to be 8. And then secant x, and then we're going to get another secant tangent factor. So it looks like it's going to be secant squared tangent cubed. Then we need to differentiate this, so we're going to get plus 8 secant, we had secant squared, differentiating a tangent under chain rule gives us another secant squared, so secant to the 4th, and then tangent x. And then this piece, just chain rule, so 8 secant cubed, but we're going to get a secant tangent, so secant to the fourth tangent x. Okay, now in absolute value, we can stick that stuff in absolute value. So absolute value, fourth derivative, is 8 secant squared plus, 8 secant squared times tangent cubed plus 8 secant to the fourth tangent plus 8 secant to the fourth x tangent. Now, this is a hard one to sort of see what's going to give you the largest value. Of course, all this is an absolute value. My apologies. So this is not probably something you would see on like an exam or something, but I thought it was interesting because it's tangent and it's worth seeing at least a Taylor approximation for tangent. What you should remember, though, is that tangent sort of looks like this, which means that as we drift further from the center, it gets larger and larger. So tangent is going to be largest at like pi over 4. Technically, it's the same at negative pi over pi over 4 if we only care about absolute value. Secant, well, remember secant sort of looks like this, and then it has these like weird pieces here. Since we're near 0, it also gets larger and larger. So all of these are maximized at pi over 4. So we're going to let m be the fourth derivative at pi over 4. Now, at pi over 4, tangent of pi over 4 is 1, and secant of pi over 4 is 1 over cosine of pi over 4. Cosine of pi over 4 is root 2 over 2, so that is going to give us root 2. So anywhere there's a secant, we can put a root 2. Anywhere there's a tangent, we can put a 1. So we're going to get, all of this is going to be positive, so we don't need our absolute value bars. 8 times 2, because root 2 squared is going to be 2, times 1 plus 8 times 2 squared times 1 plus 8 times 2 squared times 1. So we put all that together. That looks like it's going to be 16 plus 32 plus 32. Looks like we should get m equals 80 here. So our m needs to be 80. All right, let's go ahead and then pop that in. So in terms of our actual error formula, R3 of x in absolute value should be less than or equal to that 80 over 4 factorial and then pi over 4 to the fourth. If we actually type that in and we see what we get there. So again, this is something that's got to be done on a calculator because of that pi over 4. But if we do that, we'll see that the maximum error is about 1.27. So the maximum error when doing an approximation anywhere from negative pi over 4 to pi over 4 is going to be capped by 1.27. So actually, the true accuracy is way, way better than that. Like we said, if you actually compare on like a calculator, we got 0.542 when estimating tangent of 1/2. The actual thing is about 0.546, so we were only off by about 0.004. This is a way overestimate, but it is the maximum error that could possibly occur. So again, no reason to say that this Taylor inequality tells us the exact error. It just gives us an upper bound on the worst case for our approximation. So this wraps up section 11.11. So at this point, we've seen how to build exact representations of different functions using Maclaurin and Taylor series, and how to build approximations using only finite polynomials. This wraps up everything we wanted to say about series overall. This finishes chapter 11. After this, we'll be going sort of backwards a little bit, taking a look at chapter 8 and looking at some more geometric properties that can be determined based on integration.